everyone, this is lecture video 21. We will cover mean value theorem in this lecture. This theorem is the generalized version of the Rolle's theorem, which was explained in the previous lecture video. In fact, mean value theorem is the slanted version of the Rolle's theorem. It guarantees that there is one point on your graph whose tangent line is parallel to the line segment from A to B. Okay, let's look at the formal statement now. Suppose that your function is continuous. You have a continuous function here, f of x. This is the main assumption. And it should be differentiable on the open interval, just like we had in the Rolle's theorem, right? So maybe I can start writing assumption box and conclusion box as usual. F of x should be continuous over the closed interval AB, and f of x should be differentiable over this open interval AB. These are the assumptions. Okay, so let's create a box here for the assumptions. Then what is conclusion? And conclusion says that there is a number C between A and B. There is C between the point A and B. Okay, we are looking at this point C now, where the tangent line is parallel to this line segment. Since they are parallel lines, like this, okay, let's indicate that they are parallel, they have to have the same slope, right? So these two lines are parallel. Lines are parallel, which means that they have the same slope, right? So let's say the slope of this is m1, the slope is m2. So since they are parallel, we should have this. The first slope is given by this, f prime c, and the slope of this second line, let's try to find it, okay? So the slope of this second line is in fact given by this expression here, right? Is it length of this part divided by the difference of B and A. So let's write it down. F of B minus f of A over B minus A. What is this? This is the slope of the second line. Right-hand side, left-hand side is the slope of the tangent line. Okay, let's also put this as the slope of the second line between the points A and B on the curve. So since they are parallel, their slopes have to be the same. That's why the conclusion is this equality here. Okay, there is a C between A and B where f of C is given as divided by this. This is our conclusion box. As long as the assumptions hold, then you will have this conclusion. You can apply mean value theorem to use this conclusion. Okay, also here, let me put, this is the slope of tangent line, and right-hand side gives you the slope of the second line. They are the same because at the point C, they are parallel. Okay, this is what mean value theorem is. Now let's see how we can apply it. This is the example which we can apply mean value theorem. Okay. So in this example, there is a car accelerating, and this graph gives you the acceleration of that car. If a car accelerating from 0 takes 8 seconds to go this much feet, its average velocity over this 8-second interval is what? Let's try to find out this first. We want to compute the average velocity of the given car, right? This corresponds to rate of change of the function given here as f of t. Okay, what is that? How do we compute the rate of change? So we want to compute the rate of change of f at which interval from 0 to 8. Over this interval, we want to compute it. So over this interval, meaning that you will divide the value, you will take the differences of the values and divide them by the difference of points like this. So what is the result? The image of f8 is 352 divided by 8. So the result is computed as 44 feet over seconds. This is the rate of change of our function over that given interval. And the rate of change, if you remember from one of the first lecture videos, this is the slope of the second line. Second line. So if your function is continuous and differentiable, now time to apply the mean value theorem at this point. So what we know about mean value theorem, look at the assumptions box. These are the assumptions. And this is the conclusion. If your function is continuous and differentiable, let's check. You see this is a very nice graph which is continuous over from 0 to 8 and also differentiable as there is no corners, holes or something. So I will apply mean value theorem here. First of all, let me indicate that I check the assumptions of the theorem. F is continuous over here and F is differentiable over this open interval. Then, now I check the assumptions, time to use the conclusion of mean value theorem. By mean value theorem, what do I have? There is a number C between 0, 8 such that f of c, is given by, I am applying this part now, f of c is this slope of the second line which we have computed over here already. So f of c is f of 8 over 8 minus 0, which is the slope of the second line, Okay, so here, this part is the slope of the second line, where the left-hand side gives us the slope of the tangent line. And left-hand side is in fact the slope of tangents. Since their slopes are the same, we understand that the tangent line and the second line have to be parallel lines, okay? So let me use another color for the second line, like that. So this is our tangent, this is our second line. Second line is also called as the chord from A to B, Okay, this is tangent line. Mean value theorem tells us that, guarantees that there is one point between 0 and 8, which is the point 5 in our example. So C is 5 in this particular example. There is one point between 0 and 8, which is C equals 5, whose tangent line is parallel to the second line drawn between the point 0 and the point with x coordinate 8. They are parallel. So what makes that there is at least one tangent line like this, which will be parallel to this yellow line? Mean value theorem guarantees this for us. So this point C is a special point. What is special about it? At that point, if you draw a tangent line, you will find a parallel line to this yellow one, so that their slopes are equal and f prime c is given as the slope of the second line, which is computed like this. Okay. So let's move on. These are corollaries of mean value theorem. Look at the first one. If f prime is 0 at each point of an open interval, then what happens? If this is the case for all values of the interval AB, then you can conclude that your function is a constant function, in fact. Okay, this is a corollary of the mean value theorem, meaning that you can easily make a quick proof of it by using mean value theorem. So let's put here a quick proof. Okay, so what we know about the first derivative, we know that the first derivative, which is given as this by the mean value theorem, b minus a, is always 0. We know that this is always 0 for all x values in this interval. So then what do we have? To have this ratio always 0, we need to have that f of b is always equal to f of a for all values of x inside this interval, right? This proves that since all the values of your function are the same over this interval, so let me draw a picture. These are always the same for all x, meaning that you have such a graph. No matter which x you choose, you find the same image. So this proves that f of x has to be a constant function, okay? So look at the second corollary, please. It says that this time we have two functions, f and g, whose first derivatives are the same. If this is the case, okay, let me write this down once more. If this is the case for all values of x over in an interval, then you know that these two functions differ only by a constant, okay? They differ only by a constant. How do we know this? Because if you take the difference of them, since they are equal, we know that they are equal. The first derivatives are equal. Take the difference, you will get the 0. So if derivative of something, okay, this is what? This is in fact the derivative of this difference function. If it is 0, then by the previous corollary, first derivative 0 means that the function is a constant function. Then from here, you understand that f and g differ by just a constant like this. Okay, this is also a quick proof of this corollary. And what we have here, we have an example, f of x whose derivative is sine x and whose graph passes through this point. We want to find out which function does this thing. Okay, what do we know? First derivative is sine x, and one more information is given here. Our function takes the value 2 at the point 0. Okay, let's use the corollaries that we have just covered. If the first derivative is sine x, then we can say that f of x is what? You can just think of like, what is the function whose derivative is sine x? So it should be like this, minus cosine x plus c, because you know, derivative of minus cosine x sine x, derivative of f is the same, so they should differ only by a constant like here. Okay, so now we need to find the constant number c. To find this constant, we can use the given point here. Use this information. Okay, now I will insert x equals 0 to my function. Minus cosine 0 plus c. This is supposed to be 2, right? Okay, what is cosine 0? It is 1. That's why from here c is solved as 3, which completes our function. a function whose derivative sign is sine x and who passes through this point is this function. Okay, now, in the last part of this lecture video, I will talk about natural exponential and natural logarithm functions. Let me write them down. Natural exponential and natural logarithm functions. Natural exponential function is this one. Natural logarithm function is ln x. So I will try to create a table for both of them, showing you the most important properties of them. Before completing this table, I want to put a recall or remark here. So there is also the general logarithm function and the general exponential function. What are they? Let me remind you them. General exponential function and general logarithm function. Okay, let me. And general logarithm function, they are a to the power x and logarithm base ax, right? If you use this number here, a is a random real number. You can use any real number there, okay? If you use this real number a as the spatial number e, you know this number, right? It is kind of 2.7 something. It is around 2.7. So if you choose a as the spatial number e, then these general exponential and general logarithm functions becomes your natural one, exponential and natural logarithm functions. So then you call e to the power x and, okay, let me write this part as this. So then you call this one as the natural one, natural exponential function, and the other one, logarithm base ax. We have a spatial notation for this thing as ln x, and this is the natural logarithm. It's called as the natural logarithm function. Okay, after this remark, now we can go through the main properties of e to the power x and ln x. So first property is about these powers. So obviously you can write it like this, but it is more interesting for ln function, okay? If you have ln a times ln b, it can be rewritten as a function like this, ln a plus ln b. What about the ratios? So let's say we have e to the power a divided by e to the power b, then you can rewrite it like this. And second property here is more interesting. So ln a over b can be written as ln a minus ln b. And what about the taken powers? So e to the a power b is e to the power a times b. How it works for the ln function? So if you have ln x to the power n thing, for example, or, okay, I will write it like this, then you can take this power down to here. It is the same as n times ln x, okay? So here I can write e to the power minus x is 1 over ln e to the power x, of course. Now, their common properties, you know, what is the relation between exponential function and the logarithm function? They are inverse functions to each other. So inverse functions, okay? Meaning that if you take the composition of these two, what happens? As they are inverse functions, if you take the composition in this order or in this order, they will neutralize each other since they are inverses. Okay, so that as a result, you will just have x. This happens whenever you compose inverse functions, you just end up with x. Okay, related to these two, I can write two more items. Let's take x equals 1. So what is ln e? Then it is 1. And what is ln e to the power x? We already see that it is x, but we can also prove it by using this property of ln function. X goes down times ln e. And we know that ln e is 1, so the result is x as expected. Also, we can draw the graphs of these two functions. This is the function e to the power x. This is the graph of it. And let's put here the graph of ln x function. It behaves like this. Okay, so as you approach 0 from right, the values of ln x function go to, sorry, not plus, of course, it is minus infinity. Okay, so as we know that they are inverse functions to each other, their graphs should satisfy something, right? The graphs of inverse functions should be symmetric with respect to y equals x line. So what does this mean? Let's put y equals x line, here. So let me try. Yes, this is y equals x. Let's draw the graphs of ln x function and e to the power x function over the same coordinate system. You see they are symmetric with respect to y equals x line, okay? Symmetric with respect to y equals x line. So let me write this down and then I will stop. Symmetric with respect to y equals x line, as they are the inverse functions. So this was the last thing that I want to talk about. I stop here. Thank you for your attention.